Today we'll be looking at the chain rule, which is our next rule for taking derivatives. We'll learn a whole bunch of rules for taking derivatives in this first semester. This is another one of the general ones. So consider the function f of x is equal to 4x cubed plus 1 quantity squared, which if you expand it is 16x to the 6th plus 8x cubed plus 1. Now, if I take the derivative of the expanded form, it's pretty easy. I'm just using the power rule and the constant multiple rule and the sum and difference rules. Sounds like a lot, but I think you're pretty comfortable with it already. Now, and that gives us 96x to the 5th plus 24x squared. Now, if we were just to apply the power rule to this non-expanded form, right, we would move the 2 to be the coefficient, and we would have 2 times 4x cubed plus 1, which is 8x cubed plus 2. And you're like, well, that doesn't look at all like this, does it? However, if we multiplied both of these terms by 12x squared, we would get 96x to the 5th plus 24x squared. You're like, well, where in the world from this could we get 12x squared?
The derivative of 4x cubed plus 1.
Yeah, the derivative of 4x cubed plus 1. So what we can do when we have a composite function is take the derivative of the outside part, leave the inside part alone, and then multiply by the derivative of the inside part. That is the essence of the chain rule. So, here's what it actually says. If f is a differentiable at g of x, and g is differentiable at x, then f of g of x is differentiable, and the derivative with respect to x of f of g of x is f prime of g of x. Notice derivative of the outside, leave the inside part alone, times g prime of x. In the Leibniz notation, if y is equal to f of u and u is equal to g of x, then we can say that dy dx is dy du times du dx. Which kind of makes sense when you think about it, right? If you think about this in terms of fractions, the du's would cancel and it's dy dx. Now that's not actually what's happening, but we're taking the derivative of y with respect to u times the derivative of u with respect to x. So in words, the derivative of a composite function is the derivative of the outer function with the inner function left alone times the derivative of the inside function. So let's find the derivative of y is equal to sine of 3x squared plus 5x with respect to x. So dy dx is going to be equal to the derivative of sine is cosine. So we'll take the derivative of the outside function and we will leave the inside function alone. Times the derivative of the inside function, which is 6x plus 5. Frequently when you see these written on multiple choice questions, to avoid any confusion as to what the argument of the cosine is, because you might accidentally think that all of this is what you're taking the cosine of, a lot of times they'll rewrite it so that the polynomial part is first and the trig part is last. It's not a big deal, but I don't ever want people to get confused. I've even seen students who have done this, and then they start multiplying this out. I'm like, no. It's cosine of this, then times that. All right, so as an example, An object moves along the x-axis so that at any time t greater than or equal to 0, its position is given by x of t is equal to cosine of t squared plus 1. God bless you. Find the velocity of the object as a function of t. Okay, so the velocity as a function of t will be the derivative x prime of t. So, taking the derivative of the outside part, the derivative of cosine, and I'll usually say it this way, cosine of something, because I don't really care what the something is negative sine of that something. Times the derivative of whatever the something was, which will be 2t. So again, that's almost always rewritten so that you have a negative 2t at the front, sine of t squared plus 1. Again, to avoid any confusion. So this next one, you're like, okay, these are all sort of starting to feel the same, but look carefully at the inside part of this one. I've got 5 minus sine of 3t. Anytime you say that of, well, you need to think about that. It's not just t, is it? It's sine of 3t. What I do on these is put in another set of parentheses before I start taking the derivative. To remind myself that I have what are either of you like coding guys, computer science stuff? They call it a nested loop. You've got something inside of something else, like Russian nesting dolls. If you've ever seen those, where you take one and then there's another one inside, you take that and there's another one inside. Never seen those? You haven't? I have some. I'll show you in a minute if we have the time. So when I take the derivative, I take the derivative of the outside part. The derivative of tangent of something is secant squared of that something. Times the derivative of the something. Well, the derivative of the something, the derivative of the 5 is 0, but then the derivative of negative sine of something is going to be negative cosine of that something times the derivative of that something, which is 3. So you keep working your way inward. So you deal with the outside, leave the inside alone, deal with the next layer. I mean, this can go on for several layers, usually not more than about 3. Again, on this one, I would rewrite it. I would pull the constants out in front, the negative and the 3. So I would go negative 3 secant squared of 5 minus sine of 3t times cosine of 3t. So we can also use this parametrically to find the slope of a curve that's given in parametric notation. So, and I have trouble saying this word, parameterized. I don't know why that's difficult for me, but it makes my tongue want to snap off its rollers. So a parameterized, I overthink it. A parameterized curve, x of t, y of t, is differentiable if both x of t and y of t are differentiable and x prime of t is not equal to 0. By the chain rule, if I want to find dy dt, that's going to be dy dx, bless you, times dx dt. Well, that means then that dy dx, God bless you, is dy dt divided by dx dt. Which, when you think about it, makes sense. That's the derivative, the change in y with respect to t divided by the change in x with respect to t gives you the change in y with respect to x. So let's write an equation for the line tangent to x is equal to secant of t, y is equal to tangent of t, on the interval from negative pi over 2 to pi over 2 at time t is equal to pi over 4. Well, in order to write the equation for any line, the first thing we need are the coordinates of a point. So I'll start with that. So I'm going to have x is equal to the secant at pi over 4. Secant is the reciprocal of cosine. So this is going to be 1 over, and what is cosine at pi over 4?
Square root of 2 over 2.
Yep, square root of 2 over 2. So this is 2 over the square root of 2, which is the square root of 2. Are there not any tissues?
Oh, I didn't see any. Yes,
Yeah, it's just a lot easier on the nose.
yeah.
If you'll open the top drawer, there may be some more.
Oh, yeah.
And then for the y, we'll have y is equal to the tangent at pi over 4. That one you should know easily. Yeah, that one's 1. So I've got my point. It's the square root of 2, comma 1. So then dx dt is the derivative of secant. So that'll be secant t tangent t. And dy dt will be the derivative of tangent, which is secant squared. So dy dx is going to be secant squared of t over secant t tangent t Since secant t is a factor of both the numerator and denominator, I can divide those out. And if you want to, you can rewrite it. Secant is the reciprocal of cosine. So there's going to be a cosine of t in the denominator. Tangent is sine over cosine, but it's in the bottom. So that's going to be a cosine on top and a sine on bottom. Well, that's pretty convenient. It's going to be 1 over sine of t which is, well, I'll just leave it like that because I want to evaluate it, right? So the slope will be dy dt, or excuse me, dy dx, evaluated at t is equal to pi over 4. So that's 1 over square root of 2 over 2, which we found earlier was the square root of 2. So now we have a point and a slope. So it'll be y is equal to 1 plus the square root of 2 times x minus the square root of 2. So that's 1 plus the square root of 2x minus 2. This is square root of 2 times x minus 1. Okay, questions about that? Third period 10. Oh, wrong day. 9:45. All right, if we have time, we'll draw that. We'll come back to it so you can see that it really does work. All right, find the slope of the line tangent to the curve. Y is equal to sine to the fifth x at x is equal to pi over 3. Well, remember, when you have sine to the fifth x, what does that literally mean?
Sin x multiplied 5 times.
Yeah, or sine of x quantity to the fifth power, multiplied times itself 5 times. So that helps us to be able to take the derivative. Y prime then, we'll start with the outside part, which is the power function. So we'll use the power rule. That'll be 5 times the sine of x raised to the fourth times the derivative of the inside part, which is cosine of x. So then the slope, we simply need to evaluate this. That'll be 5 times sine at pi over 3.
Square root of 3 over 2.
Very nice. Square root of 3 over 2 to the fourth, which means that cosine must be
1/2.
1/2. So it's going to be 5 times square root of 3 times the square root of 3 is 3. And we're going to do that twice. So that's going to be 9 over 16 times 1 over 2. So that's the truly spectacularly ugly 45 over 32. Perhaps not nearly as steep as we might have expected it to be. You know, when you've got sine to the fifth, it's like that seems pretty high. The reason it's not as high as you might expect it to be is because at pi over 3, you're nearing the top of the curve, so it's started to slow down. At first, it is really going up rapidly. If you were doing it at say, pi over 4, it's going to be much steeper. Sorry, suddenly I had a memory of this problem being something that I needed to fix, and I don't know that I've ever fixed it. Give me just a moment. Yes. Let's make this last part of the u, just to make it simple, let's make it a 15 instead of a 5. If memory serves, this comes out to be something, actually I'm pretty sure, if you leave it as a 5, it comes out to be undefined. I'm like, I really didn't mean for that to happen. All right, so we're evaluating f of g prime at x is equal to 0 for this. Now, remember, that's kind of an old school notation. So what they're really asking is they're saying, find the derivative with respect to x of f of g of x. That's still screwed up. Let me see if I stole this problem out of the book and just didn't write everything down right. I apologize. But well, I don't see it. All right, let's change this to a U. And I think that will make more sense. We'll see. This problem had all kinds of problems. All right, so this can get a little confusing because you're like, oh, this is in terms of U. Could you take this and substitute it in and then work it out? Yeah, but it's really kind of ugly if you do, because you've got to raise this quadratic to the third power. That's going to take a bit of time. So instead, what we're going to do is we're going to do, all right, so with Leibniz notation, I'm going to take the derivative of f with respect to u times the derivative of u with respect to x. This is where Leibniz notation is helpful. So that's going to be the derivative of f with respect to u. I'm going to have to use the quotient rule. So that'll be u minus 5 times the derivative of the numerator, 3x or 3u squared, minus the numerator, u cubed plus 3, times the derivative of the denominator, which is just 1, all over u minus 5 quantity squared, times the derivative of u with respect to x, which is just 2x plus 3. I'm not going to spend any time at all trying to simplify that first part. What I am going to do is say, all right, well, if x is equal to 0, then u is equal to 15. So now I can evaluate this. Rather than spending a lot of time simplifying the algebra, I can just start chuffing in numbers and cranking that out instead. So we're going to have f of u prime evaluated at x is equal to 0 is going to be equal to 15 minus 5 times 3 times 15 squared minus 15 cubed plus 3 all over 15 minus 5 squared times, if x is 0, we're going to multiply that whole thing times 3. So that's going to be 10 times 225 times 3 is 675 minus 15 cubed, yikes on bikes. I don't know that one. $3,375? Oh, plus 3. So 3,378 all over 100, all times 3. So that's 6,750 minus 3,378. And then I'm going to multiply that times 3. I may need to do this whole problem over from the start. So this is 704.6. If I have done, oh no, 70.46. If I've done all of that arithmetic correctly. Okay, any questions about that?